If you recall, yesterday we had this velocity function, and I said, what are the questions that I could ask? And we had three categories. The structure that we want to notice when we're looking at this function is that I've given you the velocity. I've given you a function that I've cast as the first derivative. So I'm giving you information about the first derivative. This is what we were doing all of last week, the week before spring break, when we had the graphs and I said, here's a graph of the derivative. We're playing the game slightly differently. First of all, instead of giving you the graph of the derivative, I'm giving you a function for the derivative. And instead of just being a generic function, I am giving you some context. So we're kind of we made two changes. We've changed from looking at the graph of the derivative to looking at the derivative itself. And also we have put context. This doesn't really change the questions that I can ask given the derivative. So this does not change the kinds of questions that I could ask, and that was the point of the exercise yesterday. I'm still going to ask questions about I can ask questions about the function that you're looking at. I can ask questions about the derivative of that function, and I can ask questions about the antiderivative of that function. I could ask you to find the derivative of the function, which in context would be find the acceleration. I could ask you about I could ask you some definite integral questions, which would just be questions about position. All right, so let's talk about this. I actually want to start in the mid. So that's the structure that we're looking at. We've got on top, we've got position. We had velocity in the middle. And as our first derivative, and we've got acceleration as our second derivative. This problem, like the problems last week, we start here. If I want questions about position, that's going to be integration stuff. If I want questions about acceleration, that's going to be derivative stuff. So since we're starting here, these questions are going to be derivative questions. And these questions are going to be integral questions. That's the structure of this problem. I need my calculating machine. So what kind of questions could I ask? The most direct question, it would just be a velocity question. Just use the function that you are given. So the most direct, easiest questions to make up would be a velocity question. So in the category of velocity questions, I could ask for something like, what is the velocity of the particle? At t equals 8 seconds. That would just be evaluate the function at 8. Since there is context that I would want to put this in context, I might say something like, what direction is the particle moving? Then show your calculations, round your answer to however many significant figures. So if I could ask a question, what's the velocity of the particle at 8 seconds? In that case, we would just want to this would just be a question of finding V of 8. So 1 plus 2 times the sine of 8 to the 1.2 divided by 3. We just want to make sure our calculator is in radians. Since our calculated velocity is negative 0.567 centimeters per second, that would indicate that the particle is moving to the left. Velocity is negative, particles net is moving to the left. A related velocity question, I might say, at what time, if any, is the particle changing direction? So here, this is a question, at what time, if anything, if any, is the particle changing direction? This is where we're looking for where V of t is equal to 0. In this case, it would be best to use a graph. Although it wouldn't be too bad to solve this equation because there's only one instance of t, we could do inverse operations in reverse order. That's really only going to work since we know what the graph looks like. I'm really only looking at that first cycle of this function, even though this function is not periodic anymore since I raised the t to the 1.2 power. So I've severely messed with this function, but the way that I've messed with it and the range of t, or the domain that I installed on the function, means we could do inverse operation in reverse order. So in this case, we could, there's also the reason that I use 1 and 2, just in case someone thought to do this. So we would subtract 1 from both sides. If we look at the order of operations on t, first we did a 1.2 power, then we divided by 3, then we did the sine, then multiplied by 2, and finally added 1. So if we wanted to solve this equation, we could do inverse operations in reverse order. So the first thing that we'll do is subtract 1. And then divide by 2. Then we could sine inverse. Now the problem here is we don't want to sine inverse on our calculator because if sine of something is equal to 1/2, if sine of something is equal to 1/2, that's going to give us something in the fourth quadrant. Sine inverse for the calculator is a very specific thing. So if we do a sine inverse here, If we just did a sine inverse, we're going to get a negative value, but we don't want that negative value. So it's going to give us a negative 0.523, negative pi over 6. Sine inverse of negative 0.5 is going to be a negative pi over 6. Everybody recognize 0.523, 58, 598, 7756. We all recognize that as pi over 6, right? Totally. Totally. No, we just know it's pi over 6 because sine inverse of sine of 30 is 0.5 and 30 is pi over 6. So it's like when we learn radians, we learn the radians as a second language. So we think in degrees and then we translate that to radians. It's like when we learn a second language, but we're still slow at it because we're translating it to our native language and then going back. So this is one of those scenarios where we have to know what we're dealing with. Because at this point, if we just sine inverse of the negative 0.5, we get a negative 0.523. Then we would multiply by 3 and raise this to the 1 over 1.2 power. And then we get a non-real answer. But we know by looking at the graph that there should be an actual answer, right? And this is where that problem showed up. I like how when you say go to the problem and it's like, oh, this whole thing, it just puts the cursor at the end. It's like, I'll just, like with a syntax error, it'll highlight the thing. That's the syntax error problem. But here it's like, oh no, this is all bad. What are you thinking? So if we just start trying to follow our nose and use the calculator to do so without remembering that sine is not an invertible function, that sine inverse is a very is restricted to quadrant 4 and quadrant 1. Then we'll just say, forget it. I'm going to use a graphing calculating machine. I can't remember. Oh, there it is. In this case, let's think about this from, let's think about the meta for this particular problem. At what time, if any, is the particle changing direction? If I'm asking this question, I am handing you a graph and I've clearly labeled where the velocity is equal to 0. I'll probably label all the points. I'd label all the points and you would have to decide which one is the velocity equal to 0. I would be like, oh no, they're trying to solve it by hand. That would not be the intention, which means I would probably leave this off of the problem. But using a graphing machine, this happened, I have to go by my reference, 7.374. So the efficient way to do this problem would be to look at the function on a graph and see where the velocity is equal to 0. When the velocity is equal to 0, then the particle is changing from moving to the right to moving to the left, or moving from the left, moving left to moving right. The point of asking this question will be to ask you to recognize that velocity is 0, means we're changing from right direction to the left direction. Any question? unless I made it a pit stop and I had it positive before 0 and then positive after. But you would be able to read that on the graph. Any questions? I'm pretty sure that the only reason that I brought this up, it might be the only reason I use this particular function, is that I have a trig class and we're solving trig equations. I don't think that's the only reason that this came up. So these are the possible velocity questions. Asking questions about which direction is the particle moving? Which direction is the position changing? How is the position changing? What is the sign of the velocity? In the category of acceleration, these questions, so the velocity questions are questions about the given function itself. Acceleration questions are going to be about the derivative of the given function. So acceleration questions are about the derivative of the function. So I might say something like, what is the acceleration of the particle at t equals 8 seconds? This would just be find the derivative of the function, because acceleration is the derivative of velocity, and plug in 8 seconds. The context portion of this question would be to say something, ask something like, is the particle speeding up or slowing down? Or I could ask a completely different question. Is the particle accelerating or decelerating? Here we would want to know the derivative of the function. So v prime, the derivative of 1 is 0. The derivative of 2 times the sine of something is 2 times the cosine of that thing times the derivative of that thing. So 2 times the 1.2 is a 2.4. 2.4 divided by 3 is 0.8. Oh, it's not negative 0.8. 1.2 minus 1 is 0.2, not 0.8. Cosine times t times a cosine of t to the 1.2 over 3. T to the 0.2. Yeesh. So what we want actually is here's the acceleration of the particle in centimeters per second squared. The acceleration at 8 seconds would just be plug in 8. 0.8 times 8 to the 0.2 times the cosine of 8 to the 1.2
divided by c.
At this point, we have a very messy question. Is the particle speeding up or slowing down? So at this point, we have a very messy question. At 8 seconds, the velocity is negative and it is getting more negative. So in terms of speed, the particle is speeding up. The particle is moving faster in the negative direction. So recall that the velocity at 8 seconds, the velocity is negative, and the acceleration of the particle is also negative. So it's going from negative 0.6 centimeters per second, and it's going to decrease by another 0.7 centimeters in the next second. It's going to be more negative. It's going from 60 miles per hour south to 65 miles per hour. Actually, it's going to increase by quite a bit. It's like going 60 miles per hour to the south, and then the next second be going 120 miles per hour to the south. So the particle is speeding up. This is a messy question because the particle is speeding up, the acceleration is negative. The velocity is getting more negative. The speed of the particle is increasing. Here's the end result. I wouldn't ask this question. It's too messy with everything negative. I would go through the problem and I'd say, oh, fuck that. I don't want students to have to deal with that shit. And I would move the entire problem to where the velocity is positive and the acceleration is positive. For those of you who remember the problem from yesterday, I would go for that first 3.3 seconds. Because at that point, the velocity is positive. You calculate the acceleration, that shit will be positive, and you'd be like, oh, this is speeding up. And I'd be like, oh, that is correct. That makes sense? Otherwise, we get into semantic problems. If, when you're handing a test back and you're explaining how the problems work, you have to say, well, actually, you should have changed that problem. Do you know what I mean? I'm worried about this because some of you might become teachers. You're going to graduate with technical degree or with like a scientific degree. You're going to be looking for a job. You're like, oh shit, I guess I have to teach at a high school. And you're going to be writing tests and shit like that. So you got to pay attention to these kinds of things. You know what I mean? Point is here that these questions are messy, but here's the acceleration question that I can ask. The point of the problem would be to say, do you recognize acceleration as the derivative of velocity, which is the given function, Did you find the derivative of that function? Did you plug in 8 to find the acceleration at that point? Any questions? Comments? Snide remarks? We do actually get into some interesting questions when we move up to position. Position questions will come in two different flavors. We could ask questions about distance, and we could ask questions about displacement. Displacement would be like location. Where is the particle at a certain time? Distance is different. Distance is where we ignore direction and just care about speed. So position will come in two different varieties. Displacement, which we could think of as location, and distance. This is going to be related to speed. With displacement, we care about the sign of the velocity. With distance, we care about the absolute value of the velocity, just how much velocity is there, not which direction it is going. This afternoon, after I arrive back home, my displacement will be 0 from this morning. My distance traveled will be about 10 miles. So if the question comes in displacement, or location, in this case, displacement or location at time t equals 10 seconds. This is where we consider velocity to be negative, and we can have some distance canceling itself out. That's where we just calculate the definite integral. Where is the particle? It went to the right for a while, then it went to the left, 12.9 centimeters. Since the particle started at the origin, it's 12.9 centimeters to the right of the origin. But if the question was about the distance the particle traveled, then we're going to need to break this into two definite integrals. The definite integral where the particle is traveling to the right, 7.374. And the distance that the particle is traveling to the left. And the definite integral is going to report this as negative. So I will want the absolute value of that one. So this is the to the right. This second definite integral is going to be to the left. And since the velocity is negative, definite integral is going to call this negative. So to the right, we move 14.9 centimeters. But then when we go from 7.374 to 10, we are now moving to the left, a distance of negative 1.9 meters. So if I want the distance traveled, I'll take the absolute value of that negative definite integral. I didn't do the absolute value. Just do this one. So the total distance the particle traveled is 16.8 centimeters. 14.9 centimeters to the right, plus another 1.9 centimeters to the left. The particle is a total distance located at 12.9 centimeters from the origin, but it had traveled a distance of 16.8 centimeters to some of the sometime for part of the time it was going the other direction. I don't know why I can't make sentences today. This whole thing was worked out so well in my head before I walked into the room. Oh, well. I don't know if it's a more coffee problem or a less coffee problem. I know what solution I'm going to apply. Any questions? Comments? Anyone in chemistry? Can you let me know if coffee is actually literally a solution? It's a bunch of stuff floating in water, right? So here are the kinds of questions that I could ask. All we're doing is asking those questions in context, but they are the same kinds of things that we were doing last week. I gave you a velocity function, or excuse me, I gave you a first derivative and asked for some definite integral, definite integral questions. Main thing that we want to remember from this is that the definite integral of a rate of change gives us the amount of change in the function. Since we're integrating a velocity, we get the amount of change in position. This relates to our calculus thinking, because integration is multiplication in which one of the factors is continuously variable. We are just doing distance is equal to rate times time, whereas before we were doing area is equal to length times width. All right. That's going to do it for today. We'll practice some more position velocity acceleration tomorrow. That's it for today. I will see you all on tomorrow. Everybody have a good day and thanks for playing.